Find all first partial derivatives of w in the equation x squared y plus y squared plus zw plus w squared equals 2 at the point 1, 0 minus 1, 2 using implicit differentiation. Now, what's happening here? We have our equation in 4 variables, x, y, z, and w. Set of all points that satisfy this equation is going to be a subset of 4 space. If w were a function of x, y, and z, getting our partials would be straightforward. But if you note, for some x, y, and z, okay, we put them in here, we solve for w, can wind up getting 2 points to come out, meaning w is not a function of x, y, and z. Now, we can still talk about partial derivatives, but we'll have to use implicit differentiation. So the way we do that, we're just going to assume w is a function of x, y, and z, and then we do our usual business of partial derivatives, but we need a chain rule whenever we take a derivative where there's a w. So let's see how this works. Okay, for partials with respect to x, we have 2 things that are equal. So if I take the partial with respect to x on both sides, what comes out is going to be equal. So let's go through that. Now, for x squared y, if I do the partial with respect to x, we treat x as the variable, y, z are going to be constants, w is going to be the function where we apply the chain rule. So y is a constant, so partial of this term with respect to x is going to be 2x times y. Y squared, treated as a constant so it goes to 0. Z times w, z is treated as a constant, so we just pull it out. And then if I take the partial of w with respect to x, well, that's what it is, partial of w with respect to x, and we leave it like that. That's what we're trying to solve for. Then, if I do partial with respect to x of w squared, we apply the chain rule. So the w is the inside, so the 2 comes down, exponent goes to 1, put the w back in, and then I multiply by partial of w with respect to x. So we get our equation here. Okay, note I use soft D instead of the hard D because w is going to be a function of x, y, and z, meaning there's a few variables floating around. Now, once I get to here, it's just a matter of isolating partial w with respect to x. So we put all the partial w with respect to x on one side, and then the non-terms on the other side. So we'll put 2xy to the other side as a minus 2xy. We'll factor out the z plus 2w, and then divide. So my partial of w with respect to x is given as here. If I want to consider it at a specific point, then I take our point, stick it in. So here I need x, y, z, and w, because w is not a function of x, y, and z, okay, in our original case. So I need to tell you what the w is also. So when we work that out, we're going to get a 0 over 3, which gives me a 0 for our partial at the point. Now let's do the partial with respect to y. So here, x and z are treated as constants. W is our function still. First term, x squared is treated as a constant. Y goes to 1, so I get an x squared. The y squared is going to go to 2y. Z times w. Z is treated as a constant, so we just pull it out. Then we take the partial w with respect to y. For a final term, okay, that's just a chain rule. So we'll have 2w, and then derivative of the inside is going to be partial of w with respect to y. On the other side, we take the partial 2. That's going to go to 0. So we get our equation. I want to isolate the partial derivative of w with respect to y. So we move the non-partial stuff to the other side, factor out a z plus 2w, and then I divide. So that's our partial with respect to y. If we want it at a point, we stick in our x, y, z, and w. Okay, note we'll need the w for the denominator. So it's going to give me a minus 1/3. Finally, let's find the partial with respect to z. So here, x and y are treated as constants. W is still our function. Now, for the first 2 terms, we're just going to go straight to 0. There's no z in there. For the third term, we're going to use the product rule. So the z goes to a 1, leaving me with a w, and then we have z times partial of w with respect to z. For the w squared, again, it's just a chain rule, so we get 2 times w partial w with respect to z. And then that 2 on the other side goes to 0. So we get our equation. We want to isolate partial w with respect to z. So we move the non-partial stuff to the other side. So it's going to be a minus w. Factor out z plus 2w, and then we divide. So we'll get minus w over z plus 2w. If I want that at a specific point, we put our values in. What comes out is going to be minus 2/3. As a final note, let's remind ourselves of what these partial derivatives mean. Now, suppose we consider partial w with respect to y. Then what are we doing? Well, we have our subset of R4. Okay, here I'm going to focus on the w and y axes, and then we'll just push the other axes onto this last axis. So x and z are being treated as constants, so we're not worried about changes in them. Now, at our point, we can take the plane that's parallel to the YW plane. That's going to intersect our subset and a curve. And then if I pull that plane out, put it off to the side, we're just going to have something that's a one-variable calculus problem. So our partial derivative of w with respect to y is just going to be the slope of this tangent line above our point to our curve. So it's the usual interpretation of derivative.